when we are talking about this data transfer, so it can be classified into two categories. So, one category is synchronous data transfer, when the transmission between the two devices they are with respect to a common clock. So, if we have a common clock, like if this is the transmitter and this is the receiver. So, this data transfer takes place and they are driven by a common clock signal. So, this type of transfers, so they are known as synchronous data transfer. So, a sequence of synchronizing signal can be sent before the communication takes place. So, like for telling that okay, I want to send data now. So, that way, so this clock is acting as the synchronization signal. So, that way, or it may be that there are some signals that are sent from transmitter to receiver telling that it is going to start the communication, and the bit rate and everything can be set. And this is usually high speed data transmission. So, we have got transmission of the range of 2 kilobits per second and things like that, and it is a message based communication. So, synchronization occurs at the beginning of a long message. So, if you are sending a long message, at the beginning some synchronization bits are sent, so that the transmitter and receiver they get synchronized, and then the data transfer starts. So, this way we can have this synchronous data transfer. On the other hand, we can have asynchronous data transfer, where the transmission can occur at any point of time. So, it is character based transmission, every character will be sent separately, and it is low speed transmission, less than 20 kilobits per second. However, the advantage is that we do not need any synchronization sequence between the transmitter and receiver. So, that way the communication overhead is less, you can say. So, the generally the standard that is followed is like this. The line is normally at logic 1. Okay. So, when no transmission is taking place between the devices, so line is at logic high. So, it is like this. So, it is at logic high. Then, so this is the one is called mark, and logic 0 is called a space. So, when you are transmitting a bit, so the bit So, when you are transmitting a bit, so this bit may be logic high or logic low. So, we can have this two devices. So, this bit that is transmitting, so it may be 1 or it may be 0. So, in the transmission terminology, so this 1 will be called a mark. This is the technical term for mark, and for 0 it is called a space. Okay, some sort. So, this is a very old nomenclature, but that is followed in the literature. So, we have got this mark and space, and transmission begins with a start bit which is low. So, you can understand from this diagram that we have got this thing, initially it is high, and then this low, it means that this is the start bit, fine. Then after that 7 or 8 bits are transmitted representing the character that you want to transmit. So, this D0 to D7 are the bits that are transmitted. So, normally we are transmitting in ASCII code. So, ASCII is a 7 bit code, or if you go to extended ASCII, so it is 8 bit code, or then there is a EBCDIC coding which is 8 bit code. So, that way whatever be the coding, so those 8 bits will be transmitted, and the transmission is concluded by 2 stop bits. So, these are the 2 stop bits which are high for 2 successive clock cycles, and then successive clock 2 successive bit times, and then they will be taken as the end of the transmission. So, again for if you are going to transmit the next character, so again you have to send a start bit and send the next character. So, this way this asynchronous data transmission will take place. Now, between the in this transmission, so we can have this type of classification: simplex, duplex, and half duplex. Okay, simplex, half duplex, and full duplex. So, simplex is one way transmission. So, it from there are 2 devices, and out of them one of them is a master, other one is a slave, and data transfer is always either data transfer is always from the master to the slave, or it is always from slave to master, only in one direction. Okay. So, it cannot be in both the directions. Half duplex means the transmission can take place in both the directions, but at any point of time. So, it is in a single direction only. So, that is half duplex type of communication. And we have got full duplex where the data flows both ways at the same time. So, we can have this. So, half of this simplex transmission means, so it is, so the direction is fixed. So, if this is the transmitter and this is the receiver, the direction, the transmission is always from the transmitter to the receiver. Then in case of so it is very simple. So, only one wire is needed to connect between the devices. So, typical example may be a communication from computer to printer. So, of course, there are some status checks and all that. So, ignoring those status checks, actual the data transfer is from the computer to the printer only. So, that way it is a simplex type of connection. Then half duplex connection. So, here this data transfer can be both in both the directions. Okay. At some point of time it is from device 1 to device 2, sometimes it is from device 2 to device 1. So, typical example is the telephone line where two people are talking. So, at one point of time the line is in one direction only. So, and it switches continually, and so that at some point of, for some time it is in from person 1 to person 2, and again in the next slot it is from person 2 to person 1, but this happens so fast that we may not be able to understand that switching. So, in this case also one wire is sufficient, and the best connection is the full duplex connection. So, you have two wires will be needed. So, we have transmitting and the transmission and receiving wires. So, they are separate. So, we can have the transmitter and the receiver. So, this is the device 1, this is device 2. So, this is transmit data, which is known as TXD, and this is the receive data. Similarly, for this side we have got the transmit data, we have got transmit data here and the receive data here. So, this way we can have this transmission and receiving taking place simultaneously. So, in this case two wires are necessary, one for transmission and one for receiving, and so it is like communication between two computers. So, we have got this full duplex communication. So, next important thing is the rate of transmission. So, parallel transmission. So, all 8 bits are sent simultaneously. So, if you are sending one character at a time, so even for parallel communication all the 8 bits will go together. For serial transmission, the bits will be sent one at a time. So, one bit will go at a time, and so it will take longer time. So, we have to because the bits will go serially, and since that transmission and receiving devices, so they may not be operating on the same clock. So, we have to have an agreement like how long is one bit time. So, if you look into this diagram, you see that I have said that okay, this is D0, this is D1. So, apparently it seems that this is this D0 D1 is a demarcation point, like when D0 ends and D1 starts. So, there must be an agreement about what is the duration of this bit D0. So, what is the individual bit durations. Okay. So, this transmitter should activate the value of D0 for that much time, and receiver should expect that value of D0 within that time. So, that way that agreement should be there. So, there needs to be an agreement on how long each bit stays on the line. So, rate of transmission is measured at bits per second or baud. So, how many bits you are transmitting per second. So, once this bit rate is fixed, okay, bit rate is agreed upon, the transmitter and receiver can find out what is the bit time. So, for that bit time the individual bits will be sent. So, we have got for a certain baud rate how long should it each bit last. So, you can find out like baud it bits per second. So, seconds divided by bits is 1 baud. So, at 1200 baud a bit will last 1 by 1200 or 0.83 millisecond. Now, this term baud is slightly misnomering here, because in communication technology, so this baud is the symbols per second, but here we are taking each bit as a symbol. So, we will be simply talking them as bits per second, keeping in mind that baud is actually symbols per second. So, this 1200 baud rate, so we can say that individual bits will lie for will be there for 1 by 1200 0.83 millisecond. So, this bit timing is fixed, and then to transmit a character, so we want to send this character A over serial communication line at a baud rate of 56.6 kilo. Now, first of all, we find out the ASCII of A. So, ASCII of A is 41 hex, that is 65 decimal. So, this is the corresponding 8 bit pattern. So, now we have to add one start bit and two stop bits. So, first this start bit will go, then this bit pattern will go, and then two stop bits will go. Total 8 plus 9, 8 plus 1 9 plus 2 11 bits are to be transmitted. Okay. Now, at 56.6 kilo baud rate, so the each bit timing is 17.66 microsecond, and so we have to set up a delay loop for 17.66 microsecond after sending one character serially. So, we have to wait for this much of time, and after that only we should change to the next bit. Okay. So, we have to set up a loop for this 17.66 microsecond, and then and set the transmission line to different bits for the duration of the loop. So, that way we have to do the serial transmission. Another important issue with the serial transmission is the error checking. So, there can be various types of errors that can come while transmission is taking place. So, some of the bits may be modified, some messages may not be received at all. So, like that, so there are different types of errors depending upon the transmission policy that we are following. So, we have to have some additional information sent to check at the receiver whether this transmission had some error or not. So, there are two very popular techniques for doing it. One is called parity checking and another is the checksum. So, parity checking is actually checking whether the total number of ones in the bit stream that has been transmitted is even or odd. So, two systems, that the two devices, before starting the communication, they can agree upon the policy, like they can say that we will accept odd parity, means the number of ones transmitted must be odd, always odd, or they may agree upon an even parity, that telling that number of ones transmitted is always even. So, if this is that bit stream that is transmitted, so if this is the bit stream, sorry. So, if some bit stream is transmitted in that bit stream, so we can say that okay, if this is the bit stream to be transmitted and this bit stream has got say even the odd number, say even number of ones. So, bit stream may be 1 1 0 1 1 0 0 0, this may be the 8 bits transmitted. So, we have a parity bit at the end of it. So, this bit is called parity bit, and this parity bit, so if we say that we will follow odd parity, then this bit will be set to 1, and if we say that we will follow even parity, then this bit will be set to 0. So, at the receiving end, if any of these bits get corrupted, say this bit has changed from 0 to 1. So, when you compute the parity at the receiving end, so it will not match. So, we can check that there is a problem with the the bit stream that has been transmitted. So, though we cannot detect like what exactly has gone wrong, but we know that something has gone wrong, and we can try out a retransmission of the bit stream. So, another possibility is to use some checksum. So, this parity is very rudimentary type of check. So, checksum means it computes some polynomial based on this bit stream that has been transmitted, and the remainder of the polynomial, so that is added at the end of the bit stream to as a pattern, and at the receiving end we again check it. So, the multiple errors may be detected by using this checksum facility. So, they are for checking, but not correction, that they will indicate that an error has occurred, and they do not say like where and where is the error. Okay. So, that cannot be told by these schemes. So, next we will see the parity checking. So, the number of ones in the as I was telling, so make the number of ones in the data odd or even. So, ASCII is 7-bit code. So, we have got 1 bit extra. So, bit D of the parity info. So, we can 7-bit ASCII code is there. So, we can add another bit for parity information. So, making it total 8-bit. Now, for even parity, the transmitter will count number of ones in the data. If the number of ones is an odd number, then this bit D will be set to 1 and make the total number of ones even. And if the receiver will calculate the parity at the received message, and it will again calculate the value of D, and if the calculated value matches with the received D value, that means it will assume that there is no error. Of course, it does not guarantee, because so if multiple bits got corrupted, then there may be problem, but in general, so for most of the cases, so this may be correct. So, when you have got larger blocks of data transmission, so for example, you are transmitting data from disk, okay, to the computer or to the memory, then there can be more number of so if you are relying on this parity and all that, then after transmitting every bit, every character, you have to do this parity bit, okay. So, that may be overhead may be high. So, instead of that, so after transmitting one block of data, so we add the check bits, okay, that is the checksum. So, transmitter adds all the bytes in the message without carries, and then calculate the 2's complement of the result and send that as the last byte. So, this is one possible way of calculating checksum. The other one I was telling is by means of some polynomial. So, the entire message is represented as a polynomial, and then it is computing some remainder. That polynomial is divided by a fixed polynomial, and it will be the remainder is put as the checksum. So, that is other policy. So, this way whatever be the policy, so ultimately it comes up with a signature, okay, and that signature or the remainder, whatever we call it, so that will be put at the end of the message, and the receiver will so that and this signature will be checked at the receiving end. So, for the policy where all the bytes were added, like the policy that is detailed here, all the bytes are added, and the result we compute the 2's complement of the result and send as the last byte. So, what happens is that we are after taking the sum, we are negating the sum and sending it to the receiver. And the receiver, after adding all the bytes, so it will get the plus of that sum, whose sign will be positive, and when the last byte will be added, the result should become 0. If the result does not become 0, that means there is some error. So, that is why it is called checksum type of thing. So, it is putting the checksum value at the end of the bytes that are transmitted. A very standard communication protocol that is used for quite a long time, since 1960s onwards, is the RS-232 type of protocol, and there are many variants of it. Say we have got 422, 489 like that. So, this is a communication standard for connecting computers to printers, modems, etc., and it is defined in 1950s. Okay. So, it uses to the voltage levels plus 15 volt and minus 15 volt. So, minus 15 volt is taken as logic high and plus 15 volt is taken as logic low. So, you see that when we are talking about 8085, so it cannot have minus 15 and plus 15 volt as output. So, we need some other power supplies for giving these values. Okay. So, that is a different issue, but the standard takes it like that, and in fact, this is a range. Okay. So, this minus 15 is actually minus 4 to minus 15 and plus 15 is plus 4 to plus 15. So, this speed is less than 20 kilo baud rate and restricted to the distance also less than 50 feet or 15 meter. The original standard uses 25 wires to connect two devices. So, but many of those wires are not connected for in communication, because so these 25 wires, so this interface was very, I should say, very robust type of connection, and many times we do not need that much rugged connection. So, if the device, if the two computers are located close to each other, then we do not need so rigorous connection between them. So, only few of wires may be sufficient. So, it may be brought down to 3 wires in the best case. Okay. So, what about the software side of this serial transmission? So, software for it is doing it like this. So, the transmission line is at logic 1 by default. So, as I said that the line is logic high, then it has to transmit a start bit to for one complete bit length. So, bit length is decided by determining that bit timing. So, from that we can send a start bit for that time, and then we can transmit the character as a stream of bits with appropriate delay. So, after transmitting every bit we have to wait for the bit time before changing it to the next bit. After that we should calculate the parity and transmit it if needed, and transmit the appropriate number of stop bits. So, this again these are all programmable, like how many stop bits, then what is the baud rate. So, all these are programmable. So, if these things are agreed upon to between the device and the processor, so based on that it can do the transmission, and then the transmission line will return to logic high. So, this is the if you are developing the software for doing transmission, so these are the steps to be followed. So, this is the protocol, this is the diagram, the schematic diagram that you can see, that in case of 8085 in the accumulator register. So, we can put the value on the D0 line, the bit that we are trying to transmit. So, this is the start bit that we are transmitting. Suppose so start bit should be 1, so sorry, start bit should be 0. So, we are and this accumulator has got the 8 bit pattern that we want to transmit. Okay. So, after sending the start bit, so we will be sending the first bit. So, this D0 is put onto the line, and that is going to after that there is a shift. Okay. So, this shift will take this 0 to this, okay, and this one will go out. So, this 0 will be transmitted next, then this way all these bits are transmitted, and when this one comes, so this one comes, then it will be coming like this. Then after that this again 7 bits, so 7 bits is D0 to D6, so that is done, and then the again another start bit may be sent, and this communication will take place. So, that way it will be taking place. So, the flow chart is like this, that set up the bit counter, set bit D0 of A to 0. So, for the start bit part, then we wait for the bit time. Okay. So, this is the that will help us in transmitting the start bit. Then we get the character into the accumulator, then wait for the bit wait for bit time. So, then we so this is in a loop now. So, of course, you can say that okay, you are waiting for 2 bit times here, but this may be brought down also. Rotate a left and decrement the bit counter. So, we rotate left. So, this next bit will be coming to the D0 pin, and then we will be transmitting that bit there, and so it will this way it will go on. Then the so this way it will go on until the all the bits are transmitted. So, when we come to the last bit, so it is also last bit has been transmitted. So, we add the parity bit, and the parity bit will be transmitted, and then we will send the stop bits for ending the transmission of the character. So, for the reception part, for the receiver part, so it will wait for a low to appear on the transmission line, because receiver it will see that line to be active to be high when there is no communication, and when a transmission is going to start, then this line is brought low. So, that will indicate a start bit. Then it will read the value of the line over next 8 bit lengths. Okay. So, next 8 bits, so it will get over the every bit time it will sample the line. So, it normally samples the line at the middle of the bit time to get the value that is available on the data line. So, there all the 8 bits are received, then it will calculate the parity and compare it to a bit 8 of the character. So, up to bit 7 is the ASCII code, and bit 8 is the parity. So, it will compute the parity and check with the bit 8. So, if they are matching, then then it is fine, and if it is not so, then it will check, it will tell that the character received is not correct, there is error. So, some higher level activity has to take place, and then it will wait for the appropriate number of stop bits. Okay. So, you will check that 2 stop bits if it is agreed upon, then or if it is agreed upon that only 1 stop bit will be sent. So, so it will wait for the appropriate number of stop bits, and then that will end the transmission of one character. again for the next character another start bit, it will wait for the start bit to come and it will go like this. So, serial reception will be like this, that first this bit on this bit D7. So, it will be getting this 0. So, this 0 will be shifted, okay, and then the accumulator content will get shifted this way. So, ultimately the pattern the bit stream that we have sent. So, 0 1 0 0 0 1. So, this bit pattern will be appearing onto the accumulator. So, first it gets this start bit, then it will get this is the first bit D1 D0 that is received, it comes here finally. So, initially the 1 came and then ultimately that 1 got shifted. So, this 1 is coming here. So, this serial reception is like this. So, it should read the input port for start bit. The start bit is not there, then it will wait in the loop. If it is yes, then it will wait for half bit time, and the bit is still low, then it will wait for, it will check when the start bit goes high. When the start bit so just if it is not low yet, that means that was a flicker, okay. So, that was a flicker, so that is not accepted, and if the bit is still low, that means it is really a start bit. So, that start bit counter is set, and then this it will go to the wait for bit time, read the input port, decrement counter, and this process will go on till the last bit has been received. Check parity for the bits that are received, and then that will be the end of the transmission.